All right, let's go ahead and get started. So before we get started, I kind of need a favor from y'all probably. So yesterday during my other class, the official school laptop took a dump, and so now it no longer displays. So I'm using my personal laptop today because RCC doesn't want to put a second monitor on the podium, doesn't want to do this, doesn't want to do that. So they provide a lot of barriers, unfortunately. So I'm going to be asking my dean for another laptop, and that's probably not going to go over well. So that's where I need y'all to say why you like this so much, right? Why it's essential, because the whole complication, right, is that obviously I'm streaming live, and that's also being recorded to YouTube simultaneously. Otherwise, if we were on Zoom, that's more difficult to make that recording readily available. And then in addition to that, if you go to Tony Cremo's lectures, well, that's the laptop that is used. So I think on that note, I'm trying to come up with another solution for Tony, but for our class right now, the OneNote wasn't even loading on the school laptop that I'm like trying to Frankenstein now, because I stole these science laptops now, and that's what I was trying to Frankenstein for your class, but it didn't work out, so I had to use my own, which isn't really ideal. So yeah, that's kind of where we're at, just kind of taking it day by day now, but that's why the notes look a little bit different, slightly, and then I will have to reshare these, so obviously the sync is messed up, so I'll fix that shortly, so yeah.
So how do you want us to advocate for that? Do you want us to write something or email it to them?
That's what I need to figure out. I know there's new reviews that just opened up for like course evaluations. So at the very least, like talking about them in course reviews. Otherwise, because the other problem is like Dusty sometimes like helps us get stuff done, but Dusty is like out of town this weekend when this like emergency cropped up. So so basically I haven't asked yet, so I don't know how it's going to go, but I just have a feeling they're going to say no, because I've had issues in the past with trying to get the laptop and like explain why it's necessary. Otherwise, I'd probably do an announcement and like just give you my dean's email if it comes down to that. So that's why I'm kind of like letting you know where we're at, why, and then what might happen. Yeah, because I'm pretty sure they'll try to push back, but not trying to be negative, but it's just past issues of no support for this. Yeah, because it was only because of Dusty that we even got a laptop in the first place, and he kind of slid it in there to help y'all out. All right, so I'll keep y'all updated, and on more disappointing news, oh no, okay, that was fine. We're probably, sorry, I knew I didn't look at everything. My Wacom isn't mapped properly. Okay, there we go. So probably no field trip, just because I can't get anything lined up. So it's kind of obviously already not doing too well. But then, I had mentioned the Rogue Creamery, but then they only wanted to do a tour on Wednesday, so that didn't really work. So that's kind of unfortunate. So that means, so for week 9 then, we'll probably do that ice cream impromptu lab. And so we'll probably, I might try to write up something, but the idea is we can either compare like the rock salt method versus liquid nitrogen, just kind of how fast that is, and maybe taste testing it, of course, to appreciate the ice crystals. But then I was also thinking, like, if people want to like try to make their own ice cream, so like I mentioned, the cool thing about liquid nitrogen is it's pretty tolerant of other ice cream mixtures. So that means like if you're lactose intolerant or vegan, then like the coconut milks, the almond milks, like those all work then with liquid nitrogen a lot better than trying to do it with the rock salt method. And of course, that has to do with the freezing point depression. But again, right, that liquid nitrogen makes it a lot more tolerant since it's obviously super cold. So I wanted to open that up as kind of, again, just something fun we can do week 9. We probably won't do like a lab report for it, just kind of play around and write a few observations, or like, what kind of ice cream recipes did you develop, especially if you're lactose intolerant or vegan or whatever, right? Then you can try kind of those different varieties and probably make some really good ice cream. Like last year when we did World Day, we did like, in quotes, cultural ice cream to try to obviously get away with it. And people made some pretty good like coconut vegan ice creams. Like I'm definitely a dairy person and thought that they were pretty good. So, and of course, if you wanted to bring anything else, if you're interested, you can bring your own stuff. But otherwise, we'll probably have at least like the basic ingredients. So we can make a basic vanilla base, and then, like I said, if anyone wants to bring anything extra, that's on you. And then makeup labs, trying to think. So we could probably maybe push makeup labs to week 10 potentially. So week 10, right, we'll have our presentations. And then can everyone do Thursday, or would that be too difficult for the Tuesday lab people to come in on Thursday?
Yeah, I could come in on Thursday. I think that's fine.
So I guess email me if you can't make it, since most people are saying yes. So then if we do that, which ideally I want to do everybody in one kind of poster session, so it can be one big class celebration. And I mean, our class has kind of shrunk anyways as we've progressed through the series. So yeah, let's plan for that. And then that means we could potentially do some makeups. So whatever lingering makeups need to happen. Tuesday of week 10. Or if you know that may not work for you, just email me and then we'll try to like look at some Fridays. But I know my Fridays have been a little busy this quarter. All right, so I think that's all our announcements. Well, I should have, okay, let me add bring supplies if you want something special. All right, so let's keep going then with our CHEM kind of introduction. And again, I'll try to point out like what we're going to be tested on versus kind of what we're just appreciating. And so now we want to get into alkenes. And so they are technically, well, let's just back up a little. So we're going to look at unsaturated compounds today. And so now unsaturated just means that they have at least one double or potentially a triple bond. Although we mainly see a lot of double bonds, especially if we're talking about fats. And so first we'll look at alkenes. So K-E-N-E-S.
Is that a type of unsaturated compound?
Yep, so the E refers to when you have a double bond. Again, compare it to the alkane, right? So the alkane was for a single bond. And so we could look at how to name it. So let's draw a few examples out. So we can have this compound. And so now we'll start with, again, the rules that we had from the other day. So still the same. So find our longest chain. In this case, it's a little easy to spot there. Okay, 1, 2, 3, 4. So now we have our butane chain, or our main one. Oh, galaxy. And so now we can assign priority. And so, right, we want to number our chain. And so in this case, now that we have a double bond, we want to assign priority to the double bond. So this will be 1, 2, 3, 4. And of course, right, if you had drawn the double bond over here, we would label it 1, 2, 3, 4. And so now our double bond is at the 1 position. And so now we'll have to change this to butene. And so to label it, it is 1-butene now. And then we could draw out, so 2-butene then, you can imagine. So 1, 2, 3, 4 again for our bute. And then ene, indicating our double bond on the 2. So 1, 2, and draw our double bond there. And then those would be, right, our only 2 isomers of butene. Since obviously, right, you move it over here, we're back to 1-butene. What's also important, so now we can look at this 2-butene in more detail.
You have like a 1,2-butene that has 2 double bonds.
Not like, what do you mean? So not like,
Say you have 2 double
I
bonds
mean, maybe.
right there among those 2 little branches. Would that still be butene?
Yeah, but then it would be like 2,2-butene. Yeah, but we'll look at more naming. So then, what's important about kind of double bonds now that we have to consider, and this goes back to all the little like molecular model kit choices. Oh, sorry. So let me pull up Amazon. So I have this pulled up on the other laptop. So if we look at some molecule kits, and so like I said, I really don't like these ones necessarily, just because they're a little bulky, the ones that we use in lab. So they're okay. But what's nice about them, and what they do show, is remember how they have like those long double bonds because you can put them there? And so what it's trying to show you is obviously not bond length, right? But what it's trying to emphasize is the lack of rotation. And so that's kind of the key here now with this butene. And so with this, we have these 2 isomers that would not be interchangeable. And so we have our cis versus trans isomers. And so this would be the trans isomer, where they're on opposite sides. And then we also have our cis isomer, where they're on the same side. And so there's also other names for this. So sometimes you see them referred to as Z and E. So Z would be the cis isomer, so just meaning highest priority on the same side. And sometimes you can remember it if you do a really bad fake German accent and you say Z for the same side. Again, really bad. And then trans being the E isomer. Again, they're used interchangeably.
It's also the 5th letter of the alphabet, so you know that there's 5 letters in trans, and 5 letters, that's the 5th letter.
That's a good one. So then we can have trans, and then again starting on the 2 position, so trans 2 butene, and then cis, so cis 2 butene. And again, not, so we'll just say not interchangeable. So, right, you would have to break that double bond. So that's kind of going back to when we're discussing what kind of bonds are going on, right, sigma versus pi. So we have that sigma bond that's, again, head-to-head, but, right, those pi's are through space, so we can't just rotate and break that pi bond. I mean, well, we can, obviously, if we add a bunch of energy, but that's not going to be happening on a fluxional time scale. And so then we move to alkyne. So the Y is for our triple bond then. And so we can look at some simple molecules. And so these always end up kind of looking funny. And so you might want to like redraw them. Otherwise you have to count your carbons carefully, right? Because we have 1, 2, 3. So that looks kind of funky. Again, a little more obvious to write it out and tell what the heck is going on. So that's, and again, now we have our triple bond. So we want to assign it highest priority. So 1, 2, 3. No, they mean linear. So 1, 2, 3 there. And so then we have 1 propyne. And so let's look at a picture by the way of, well, I thought this was interesting. So this is just the Wikipedia page of unsaturated fats. And then, you know, if you want to get into a debate later about health and saturated fats and blah, 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 you know, that's obviously like kind of big topic news right now. And so if you look at this, this is kind of interesting because obviously your fat is a component of a bunch of different fatty acid molecules. And so, you know, if you're trying to be health conscious potentially, so we mentioned, right, those saturated fats tend to be bad, or at least they're considered bad since they can stack. And so then kind of looking, right, like the palm kernel oil, that's generally considered not that great for you. And you can see that it's pretty high in just saturated fats. And then beef tallow, which now they're saying, right, that we should go back to frying in beef tallow. That's kind of more of a mixture, which is kind of interesting. And then it has, right, these higher contents of monounsaturated. So those are some things to consider.
Do vegetable oils tend to be higher in saturated fats?
So I think it depends on the oil too, because like then it gets into where it's like derived from, and then you get into like other synthetic arguments. But then like the other issue with some of these like fatty acids is whether they polymerize or not, which is another discussion. But then, so this is just an example of linolenic acid. And so again, you're just kind of appreciating, oh yeah, that one has some 2 double bonds there. Yeah, and I don't have a good picture because what's also not shown here is like the trans fat. And so with the trans fat, even though that has double bonds, from the way it's synthetically made, it still stacks like a saturated. So that's why some people think trans is like the worst fat. But again, right, there's a lot of science still to be discovered, I think, about food chemistry, but we can at least start looking at some foundations in here. All right, let's do a tricky naming one. So give me a second to draw this compound out. and then we'll try to put together all the naming things that we've learned. Oops.
What compound is that?
I don't know. You're going to tell me. Okay, so try to name it. so let's start to at least kind of put the pieces together. And so what did you find was the longest chain? How many carbons? 8? 10? 9? Uh-oh. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that was challenge number 1. I think a lot of people were miscounting carbons. So that's why I always say, right, number 1 advice in OChem is count and then count again. Counting is very important in chemistry, especially OChem. Like I said, your professors will be sticklers for like these little carbons. All right, so now we have our longest chain, and then I did label it in priority order. So this was a little difficult to ask of y'all. And so we generally want to assign like our triple bonds the highest priority. This one's a little difficult, right, because we have these iodines too that should also get high priority. But for the case of OChem, triple bonds, double bonds take precedence. So then that's why I did it in this order. And so then what other groups do we have on there to start naming, right? So now we need to identify groups. And our triple bond. What else do we see?
I see 2 iodines and a chlorine.
So 2 iodines, a chlorine, and then one more group is missing.
The little junction cation.
Yeah, so that's our methyl. So again, just kind of putting our pieces together. So methyl, and then iodo groups. And chloro. All right, so now we've kind of labeled them, and looking in the chat as well, so it kind of got the same thing. So identifying our groups. So if we go back to our rules, this is where it's helpful. And so now we want to assemble all our names, listing our groups in alphabetical order. And then we'll throw in, right, our prefixes if we need. So in this case, right, we have chloro, iodo, and methyl. So chloro is a first alphabetically. So then it goes 6 chloro, and then 8. So now I is next. 8, and then there's 2 of them. So we have to say di-iodo. And now 9 methyl. So that was our last group. And then now we can name our chain, and so our chain, right, again, it has an alkyne in there at the 3rd position, so 3, and then undec, of course, for 11, in case we forgot, and so undec, and then the ending to -ine.
Is there any naming convention for identifying specific radioactive isotopes within a molecule like this?
Not really. You would just say that you've like labeled one of them or something. But yeah, I mean, isotopic labeling is pretty esoteric to begin with.
It's typically done with like an asterisk, to my knowledge.
Yeah, but again, you're not going to like name it like that. It's going to be a very special case, right?
Yeah.
And the only reason why you do isotopic labeling is for some sort of mechanism experiment.
For like medical stuff,
Yeah, well, that's way different, right? So medical imaging, then you're like ingesting much larger amounts for observation, but like, and you really wouldn't use radioactive isotopes, right? So,
You use radioactive iodine if you have like.
right, no, I'm trying to tell you the difference, right, between when you're going to do isotopic labeling. Because, like I said, it's two very different scenarios. So, right, you can ingest them, yes, but I'm talking about for chemistry, you're not going to be synthesizing like an isotope dope molecule unless you're doing like a very specific mechanistic experiment, right? Because what you're going to do, and generally you're not measuring like radioactivity when you do different isotopes. So like you would use like carbon-13 or whatever. So carbon-13 is like the most common labeling, but you can dope anything. So like 15 nitrogen. But the whole point of these isn't that you pick like radioactive isotopes. I know you really like radioactivity, but you use them because they're NMR active. And then so that means that they light up a lot more. And so this goes back to, so C13, for instance, only has a 1% abundance. So when you normally do your NMR, you're only looking at 1% of your carbons. So then to track it and do mechanistic studies, they're going to label it with C13, and then you can monitor the products or whatever you're trying to do, and then you have a huge signal then and can track that carbon. But that being said, huh? Yeah, but it's also very expensive and like difficult to do synthetically, right? Because then you have to like really plan your synthesis of how can I label it such that, right, it's going to show something mechanistically or not.
Yeah, it's a lot.
Yeah, and then usually you're talking about big money, and the poor grad student is like sweating as they make their very expensive isotopically labeled compound. Oh, and then since you asked, let's try to name this one. So these compounds don't typically really form, but you wanted to know what two double bonds would be like. So see if you could try to name that one. It's drawn kind of funny, but
which direction would you start from in terms of numerical labeling?
you tell me what has to take highest priority. Too many tabs on my personal computer. Oh, I drew this funky. That's what I actually meant to draw, but you could, I guess we could name them both now that I've screwed up. No, so what I drew originally, right, were two methyls. So we can name this one. So how I originally drew it, sorry, like I said, I messed up there. So which one gets our highest priority? So our double bonds, and like I said, you really don't see this too much. I mean, it does exist. But we have 1, 2, so 3, 4. And then the way I drew it, we had a methyl here. So then I technically drew 3-methyl. And then we have these 2 double bonds, right? So we want to show them that they start at the 1 and the 2. And then we can say 1,2-butadiene. So notice how we add the di there to show that, yes, there are actually 2 double bonds. But yeah, I was just trying to show the simpler molecule 1,2-butadiene before I messed it up with throwing an extra methyl group on there. But that being said, you just don't typically see like 2 bonds next to each other. Again, you can force lots of things in chemistry. Oops. No. So what's more common is this compound here. And so this is 1,3-butadiene. And so later in OChem, or actually we'll start to like, we've touched on it a little bit and we keep kind of touching on it. But do you remember like the term conjugated pi systems? And so kind of the idea is you have to have a double bond, single bond, double bond, and like repeat that pattern. And that's how you get the conjugated system. So that's why you don't typically see 2 double bonds right next to each other. But again, obviously, right, things can be made in chemistry.
When you write it as butadiene, is that just a means of disambiguate, or is 1,3-butene its own chemical?
So 1,3-butene, that's just not really proper, right? Because you want to say that it's dibutene. Because you want to say that you have 2 double bonds, right? So that's the whole point of the di.
So 1,3-butene would kind of be meaningless. It wouldn't really correspond to anything.
Yeah, or you might just like confuse people, or I mean, they would probably figure out that that's what you're going for. But yeah, that's what the different prefixes are for. Oh, and I forgot to mention, so in my rant about what molecule kit you should buy for your future, I wanted to bring up this one just because at least when I was in college and continued to TA, this was the most popular kit that's like available in all the bookstores, but I actually kind of despise this kit. I don't know, I just don't think it's that helpful to use, but that's only because I've seen people do it. And so it's kind of weird. It's hard to get a good picture of this kit, but I don't know if you can tell. So you can kind of tell that it has these weird little snap joints. And so you have to like snap together your stereo center. And so when I've TA'd, like everyone's like popping and unpopping these things, and it's like the most annoying thing. And people are like trying to press their stereo centers together. So I don't think they're super friendly, just in terms of like being fast. Again, that's just my personal opinion. So that's why I prefer that baby Maruzen kit. So if you just look up Maruzen molecule kit, and then you want to make sure it's like the little baby one. So that I still think is the best one. But like I said, that one doesn't show you the double bond, the fact that you can't rotate. Oh no, I can't even find it. I have to look it up more. It's called like the alpha kit or something. Well, I'll post a link though. All right, so let's look at a few. Sorry, like I said, way too many tabs on this computer. That's why I don't like using my laptop. All right, so now let's switch to a few reactions. So we at least want to appreciate probably this one. Like I said, I don't want to get people overwhelmed, but this is a very common one, and this one's pretty basic. And so these alkenes can undergo, of course, different substitutions and break their double bond. And so this is a very common one that's done all the time, this hydrogenation. And it's usually run with some sort of palladium platinum catalyst. And these are very commercially available, little powder form. And you just pass it over H2 or some other, sometimes you may not pass H2 gas, but some other formal H2 source that they sell and make very commercially available. And then again, right, just hydrogenate, add hydrogen across there. So going from an alkene to an alkyne.
It goes from C2H4 to C2H6.
Yeah. And then, so same thing, these also undergo halogenation. And so again, right, they can add our chlorine. And so this is where, again, I don't want to get us too bogged down with it, but I want you to start thinking about it for OCHEM. So again, for our purposes, I'm just happy if you remember that it adds across the double bond. But we do want to start thinking about the stereochemistry and how it comes into play. And so this is important, and this is a common mechanism. And so now we're thinking of our structure, so thinking about it in 3D. And so of course butene is flat, so that's kind of, I mean, depending how you want to think about it, right, it's an issue just because, well, now I have two possibilities, right? So bromine's going to come in either from the top or the bottom. And so let's actually look at that mechanism. So this is a common, again, OCHEM mechanism. So you have your bromine, let's just say, or halogen, and it comes. And so if it's coming from the bottom, so now it's kind of blocking our bottom phase. And again, this would be very important in OCHEM. I probably won't emphasize it too much in this class test-wise. But then we form this bromonium cation. And so now it's blocked our bottom phase. And so now, this is where you get what's called in OCHEM our anti-addition. So now we have our bromine ion, right? It wants to react, it's hanging out. And so now it's going to come attack. And so whatever side it attacks from, then you can see that the bond is broken on the other bromine here. So either it adds by the blue arrows, so if it attacks this carbon, right, this bond gets broken. If it attacks this carbon, this bond gets broken. And either way, we get what's called this anti-addition here. And so again, that's just telling us we're making our trans isomer for bromine there. And so then just kind of comparing the product. And so this is where OCHEM, again, can kind of get detailed. So this is looking at our Eve conformation. And so then it's showing you kind of the difference, right? If you're looking at cis-2-butene, where they're on the same side. So again, right, showing our mechanism. So it's going to be anti-addition. And so what it's just trying to show you is you have this stereochemistry that you have to take into account depending on what conformation you started with. And so looking at this mechanism, so again, it still attacks from one side, but it's just now we have two methyl groups, right, on the same side for our cis isomer, and then we end up making what's called our racemic mixture. So basically we have different stereochemistries. And so again, just kind of appreciate this for now. Know that this is what's coming in OCHEM. And right, this is again why those molecule kits can be useful though. So you can really see this and, you know, manipulate them, rotate them around so you can appreciate that this has different stereochemistry. And again, right, you can just compare the relationships, right? You can try to rotate it in your head. So that's like the other skill of OChem is like, can you rotate in your head? Which some people can, some people can't, right? That's why get a molecule kit. Don't be too ashamed to use a molecule kit in OChem. Like, use your tools. And again, versus this one where we got the same product. So things to think about, but again, I will emphasize, we just want to focus on our halogenation here, that we can add halogen to our double bond for our context.
Are there any other elements that form backbones the same way the carbon does? Or similar to it?
I mean, not really, right? That's why we're carbon-based life forms.
Yeah.
And so then we can just see that similar reactions occur with other additions. So now this is a halogenation in aqueous conditions. And so again, same sort of mechanism. So let me draw it out. So again, you're kind of thinking about what this looks like. And so these cyclo chains can be funny. Actually, let's look at some pictures so you can appreciate. So again, you just always want to be thinking 3D with OChem, which is hard to do. And so I want to just show you the difference between cyclohexane, right? So now this is cyclohexane, no double bonds. So this molecule, right, if you look at it on paper, it looks like it's planar. It's not. So that's what I want to show you. So it has this 3D structure, and it actually has two different structures of what's called boat and chair. It'd be nice if it actually showed that. No. And then so versus cyclohexene, so right, kind of hard to tell from this drawing, but this is a good kind of drawing showing how the double bond, right, does make it planar there. So we have our localized sp2 hybridization. So, okay, so that just kind of puts it in context. And then you can tell the rest of cyclohexane here is kind of janky, but that's because we have sp3 hybridized at the other ones. So cyclohexane is a good one to kind of make a molecule of, but you'll also do that in OChem. But again, right, same sort of mechanism. We form our bromonium cation, and then what's shown here is again the OH then can attack from either the top or the bottom, and so giving us this different racemic mixture. So depending again where the OH adds, so then this bond gets broken, so you always have that anti-addition there. And so well, your exam is open notes, so I was going to say, I don't know if I'll test you on this reaction, but I'll at least kind of highlight it. So that one's a little odd. So we add bromine and hydroxide under aqueous conditions.
Is a racemic mixture just a mixture of multiple chiralities of the same molecule?
Yeah, so you can see how, right, they're not identical because of the position.
Okay.
But again, we'll save all the details of the racemic mixture for OChem, so that's what you'll get like super in depth with, but again, we're just trying to take a preview here. Oh, just trying to run out of time here. All right, so looking at other reactions, this is just to say, right, it can do it in other places. So anytime you have a double bond, again, halogen, aqueous conditions, we can make either one of these products. Again, thinking about the mechanism. So yay, it adds. We can also do hydration of our double bonds here. So now we're just adding literally water across. So H and OH. And so this is again kind of more for CHEM. So we'll put thoughts for the future. But we can still appreciate our mechanism here. And so looking at this, so in CHEM you'll have what are called, whether it adds Markovnikov or anti-Markovnikov. And so that just means whether it adds, so in this case, right, our hydroxide, whether it adds to the more substituted or least substituted carbon on your double bond. And so all this is trying to say is by our mechanism, so we have to have an electrophilic attack, aka something with electrons attack here. And so first it's going to attack our hydrogen, but then that means we're going to be left with this carbocation intermediate. And so a carbocation intermediate is best stabilized with more substituted. And so then now we have our positive charge there, and so now the hydroxide will go on and add. So again, we technically get our Markovnikov product, but for our purposes, right, we're just appreciating that we're adding water across the double bond. If you can remember the OH goes to the more substituted one, great. You know, if not, we're just, again, appreciating. Let's see, what do we have left here? So we should at least look at kind of other substitution reactions. We're kind of over time here. But looking at these, so they can undergo like a lot of substitutions, for instance. So we could start with and so if you remember, right, these phenyl groups are important. So this would be bromobenzene. And then there's only one group on there, so we don't need to put any numbers on it. And so then we can do different like nitration reactions, so adding like nitric acid to it, or again some sort of electrophile. And then you can, depending on what you add, you can kind of control your different products. And then let's at least just kind of look how to name some quickly. So if we had substituted this, and so this is, again, you hit it with nitric acid, and then you can put a nitro group on there under forcing conditions. And so now you can both refer to it either by this number position, so we could assign priorities, or you do it relative to one another. So if they're right next to each other, this is called the ortho product, or just O. And then if there's a space between them, so you could also do it on this side, right? It's symmetrical. So this is the meta product. And then if it's directly across, it's called para-substituted. So then naming these, this could be orthonitrobenzene, or nitrobromobenzene. And then this would be meta-nitrobromobenzene. And notice how all these are relative right to the bromo. So the bromo has priority 1, so bromine, heavy molecular weight, so bromine takes priority. And then P, this one would be paranitro bromobenzene. Or if you wanted to use the numbering, so this would be like 4-nitro, 1-bromobenzene. And technically, right, maybe we should have written 1-bromo, 4-nitrobenzene, but then you can start to see where you get little variations, right, in the naming, and even your bottles of like chemicals might be a little inconsistent. And so other common reactions, so it's pretty difficult to make benzene react, but you can add some sort of halogen, and then in the presence of this catalyst, so this is just a matching iron source. So if you're using chlorine, you want to use iron 3 chloride, etc. And then you can do a substitution there. So that's super useful for synthesis. And so same thing, you need pretty forcing conditions to make a nitro, but you can add nitric acid and sulfuric acid and pop a nitro group on there. And then you can do the same thing, so adding SO3 and sulfuric acid to get a sulfate group on. But again, pretty forcing conditions. And then we should at least throw up a few common ones. So this is toluene, so benzene with the methyl group substituted. I think I kind of mentioned amines, but then we have what are called anilines, so they're just benzene substituted amines, so those are pretty common. And phenyl groups, I think we've seen these in our acid-base chapter, so again that's pretty common. And then I think we'll go back to these because we're going to talk about later on probably more organic groups, but I'll at least show this one. So if you remember, this group is a carboxylic acid, but then the common name for it would be benzoic acid. So again, these different OChem frameworks are common. And then same thing, we'll draw. So then this group is an aldehyde. So then this molecule is benzaldehyde, at least again, kind of its more common names. All right, so we'll probably have to stop there in our naming fun. And so like I said, I'll have to resync the notes, and then you can take your break. Otherwise, I'll hand out the quiz if I can find it. Yeah, where did I leave it? Maybe I left your quiz on the printer. All right, let me get your quiz, I guess. So I'll be right back, and then I'll hand back the exams if we didn't get them on Tuesday.
on Tuesday.
That was the third one we did.
My coworker did those.
Hopefully that's you.
Yeah.